Hello, welcome to class 21, and today we're going to be doing some TCP/IP programming, or some UDP programming to be specific, and we're going to be talking about UDP, how that differs from TCP, and then we're going to talk about game servers, and then we're going to kind of finish up here by looking at some actual code where we implement a really simple game server and do that. And there's a dog sleeping in the background, so he will learn about game servers as well. That is Loki. He does not care. All right. Anyway, let's go ahead and get started. So first off, quick thing that we're going to talk about today is the difference between TCP, which is what we've been doing, and UDP, which is what we're going to use for our game server. And for TCP, TCP stands for Transport Control Protocol, and the UDP stands for Universal Datagram Protocol. And the difference between those is TCP, if you remember, it's reliable. Behind the scenes, it makes sure that all the packets are sequenced properly. It makes sure that any dropped ones are retransmitted. It makes sure that the order that they're sent is the order that they are received. But because it's doing a lot of those checks and a lot of that ensuring the integrity of the data stream for us, it's reliable and sequenced and stream oriented. In other words, it creates this kind of virtual stream that we just feed data in, and it magically shows up on the other end, and we can tell when it's successful. All of that extra overhead that it has implemented for us can result in it being slow. And when I say slow, I generally mean it not necessarily in the terms of the amount of throughput or the amount of data you can push through it, but more in terms of the latency, that it can slow things down quite a bit. And it can make a game that we implement with that unresponsive because of that high latency, which would be bad for certain kinds of games, like a first-person shooter. You don't want it, so you click, and then a quarter of a second or half a second later, you see the gunfire, and then a quarter of a second later, you see that show up on your screen. It would make the game frustrating and feel sluggish and unresponsive. Now, UDP, on the other hand, is fast and responsive, but it's unreliable and unsequenced, meaning that we don't have just arbitrary stream of data that we push things through, and it guarantees the delivery for us. That, in other words, this is like sending letters where some of them will get lost. The order you send them might be different than the order that they were sent, or the order they were received. Some of them might be duplicated. You might send one letter, 3 might show up at the other end. And the idea here is both TCP and UDP use IP to address and route the datagrams, the actual packets that carry the data. But the difference is that TCP adds another whole layer of processing that checks them, verifies them, if any are missing, re-requests them. If any are received out of order, flips them around. UDP doesn't do any of that. It just passes the datagrams through. So let's look at each of those in a little more detail. So first off, TCP, it manages a connection-oriented, streamed paradigm of communication, meaning that when you call TCP send and it says success, that means that it was received at the other end. And that allows us to send things in some sort of sequence, and we know that the data we put into that stream is going to pop out the other end in the same stream that we pushed the data in. So it automatically divides the stream into datagrams, automatically puts them back together on the other end. It automatically adjusts to the connection speed by changing that window size. We talked about that in a previous lecture. And that also means it's easy to send and receive data in a reliable fashion. We just call send. If it says it succeeded, we know it got to the other end. On receive, any data that comes in, we know there was no data missed between some previous receive and that receive. So that seems to do a lot of the work for us in managing that connection, but it comes at that downside of having a higher latency, and which is not good for real-time games. Now, UDP, on the other end, has no connections. It's just datagrams. You don't have to open or accept a connection. You just send datagrams out. There's no guarantee of delivery, so when it says it sent a datagram, that doesn't mean it was received. That just means it was sent. There's also no guarantee of the sequence ordering, the meaning that I could send packets 1, 2, and 3. They might be received in order 3, 2, 1. And there might also be duplications. We might get 3, 2, 3, 1, 3, 3, 1 coming in on the other end. It's not highly probable that that kind of duplication will happen, but you can get duplicates, and you can get things more likely out of order in a different order than you sent them. Also, there's nothing in UDP that adjusts for connection speed, since it's not managing any sort of window or stream. It just is passing the datagrams through. So if we need something that adjusts to connection speed, where it slows down when needed, speeds up when needed, we have to implement that ourselves. It's also up to us if we need it to be reliable. We have to come up with our own way of handling lost messages. We have to come up with our own way of sequencing. We have to come up with our own way of handling duplicates. And with UDP, we should probably also add our own check value to ensure the integrity of that data. Okay, so given all of that, TCP certainly seems easier. It guarantees reliability. It does a lot of the work for us. Why would we do it ourselves if it's already done? And the answer is that TCP will queue data until a larger datagram is ready. In other words, it's designed to kind of optimize the throughput, not the low latency. Now, you can turn on, in other words, if you send 1 byte over TCP IP, it won't immediately send a datagram with 1 byte. It'll say, I'll hold off for a while, and I'll see if more data comes in. And then when I get to a certain threshold, then I might send it. Or if a certain amount of time passes, then I'll send it. But I'm not going to send it immediately. Now, you can turn off that behavior with this TCP_no delay flag, where you basically tell it, hey, anytime I give you data, send it immediately. But even with that off, TCP can slow due to automatic resends, where it sent a datagram, did not get a acknowledgement, so it resends it again. And that delay latency could be a quarter second for a resend, and worse, if the resend packet is also lost, it would resend again. So you can have latencies in TCP that are half a second, 3/4 of a second. You can get up, and notice that for a real-time game, like a first-person shooter, that's going to be a catastrophically frustrating experience for the user. If they have somebody lined up in their sights and they click the button to shoot, and a half second later, the bullet finally fires and the person is already gone. So TCP can work for some games. Something along the lines of turn-based games like RPGs or puzzle games, or some sort of cooperative strategy game. Like, for example, a networked version of a multiplayer Angry Birds game would work okay with TCP, because you're not real-time doing stuff. You're selecting your shot, you're taking your shot, and then it's the next person's turn. So turn-based games would work fine. A game that comes to mind that it would work with would be, I don't know if anybody's played the game like Worms World Party. That would be example of a turn-based game that's player versus player. But the idea here is other games, even first-person shooter kinds of games, it could still benefit from periodically using a TCP connection for transferring game assets like the level data, the textures, skins, sounds, whatever other game assets are needed for a certain level or stage of the game. Those things might be better pushed through TCP. But for the real-time data, when somebody clicks a button on the user interface to fire, and they move the mouse and they push the key to run forward, TCP is a terrible way to do that because of that latency. And the worst problem about TCP IP, or TCP there, is we have, as a programmer, no real control over it other than turning off TCP delay. But that cannot improve our performance on the resend timeout latency, and the fact that some packets might get lost, and we don't have any control over what's going on behind the scenes with that. It just is going to happen. Now, So for real-time multiplayer games, such as real-time strategy games or first-person shooters, UDP is really the way that you want to go with that. You don't want to use TCP. It's just too slow. And when I say slow, not in the bandwidth sense, it's too sluggish. This latency can be high and it's unpredictable. Now, we're still going to use a client-server architecture. So what we want in our eventual design that we're going to settle on is we want quick updates of inputs from the players. In other words, when somebody presses a key or clicks the mouse, we want that to very quickly make it into the server. We then want to have the server take that information and update the game state based on the user's action. So in other words, the user clicked the W key to run forward. We quickly need to get that into the server and say, hey, this player is running forward in the world. And then the server needs to then update the game world and send that back to all the clients that, hey, player 1 has pressed the W key to run forward, and here's where they are in the world now, and hey, everybody needs to know where this player is in the world now so they can see where they are. Now, on the client end, they'll receive that updated game state, and then they'll render the screen to show the place where that player is. Now, one of the things, though, is that seems great, but since UDP can potentially lose packets and potentially swap the sequence of some of them, we need to think through some things, and it's going to require us to program around some of those shortcomings. But if we want something low latency, UDP is really necessary, and TCP is not really going to be an option for us, just because we don't have any control over it. Okay, so let's dig in a little bit further into the technical side of how UDP works. The UDP datagram structure looks like this, and you'll notice initially it's much simpler than a TCP datagram. Remember, TCP datagrams had all that stuff in there with the window and the flags and a bunch of stuff that had to do with how it sequences the datagrams. A UDP datagram is really, instead of 20 bytes like the TCP one, it's just 8 bytes. And it looks like this. It has a port, a source port, a destination port, just like TCP did. And then it has a 16-bit length and this 16-bit checksum. And then it has this payload data here. And the payload data can have a size up to 65,507 bytes of application data. And the reason it's that amount is if you take a 16-bit number, 2 to the 16th is 65,536. If you start with index 0, that's 0 to 65,535. And if you subtract 8 from that for this UDP header that we have here, and then another 20 for the IP header that's going to wrap around this, then we end up with this number here, 65,507. Now, one thing to note is that large datagrams like that, even though we can specify a datagram that large, most systems, the underlying network system cannot handle a datagram all as one packet or one block on the physical network that's that large. So what happens is large UDP datagrams need to be fragmented. And the way fragmenting works, we're going to look at in just a second. But Ethernet, for example, can't handle datagrams that large in a single packet frame, single physical packet frame that goes on the network. So it has to fragment those datagrams into multiple packets that still get reassembled. And so let's take a look at how that works. So here's an example. The MTU, the maximum transmission unit, that's the maximum packet size for Ethernet v2 is 1,500 bytes. So if we try to send a 3,000 byte UDP datagram, it would end up being sent across as 3 different datagrams that look like this. The first one is going to have the IPv4 header. The next one's going to have the UDP header inside of there. And then we have the UDP fragment 1, which is 1,472 bytes remaining out of the 1,500 possible. So 1,472 plus 8 plus 20. So plus 28 gets us up to 1,500. And what happens in the IP header itself, it has this MF bit in the flags, which stands for more fragments. This means, is there another fragment that then gets attached to this one? And there's also an offset that's set in there of 0, meaning this is a fragment that has ones that follow, and its offset starts at 0. And then the next one that comes in, it still has the same IP header with one exception. Has the more fragments as 1 still, but the offset is now different, saying 185. And the reason that's 185, that is the offset in 8-byte blocks. So 185 times 8 will get us up to that point where the next data needs to be stuck at the end of that one. And then the third one here will just be 48 bytes long, but IPv4 header again. But now notice the more fragments flag is set to 0, saying there are no more after this one. And here's my offset, 370. So it knows where to put this data. And at that point on the other end, when that gets received, it gets put back into the UDP datagram with this data, followed by that data, followed by that data. And if it collects all of the fragments, then it releases that as now the UDP packet. Now, remember, so in other words, one UDP transaction could result in 3 different IP packets getting generated in this case. And the larger we make this number over here, if we make that 6,000, we'll get a whole bunch more packets. We'll get 6 packets instead of just the 3. Or if I make this 30,000, then I'm going to get, instead of 3 of these, I'll get like 30 of these packets. And so think about the fact that we're dividing that up. And also I want you to think about the fact that this is an unreliable transport mechanism. Some of these could be lost. If they get received in a different order, we're okay because we have the offset to help us sort that out. But if some of these get lost, then we cannot complete that UDP transaction, and there's nothing that automatically re-requests anything. It doesn't work like that. So if we do allow fragmentation, we have a potential problem. And that problem is that UDP has no built-in mechanism for ensuring reliability of transfer. So any lost fragment will cause the entire thing to be discarded. In other words, if it gets fragment at offset 0 and then the next one but doesn't get the last one, then the whole thing gets dumped. It never gets completed and it gets thrown out. So thus, for example, if you sent a 65,507 maximum size datagram, that'll end up as 45 IP fragments. And the chances of one of those getting lost is not insignificant. And if just one gets lost, then that whole 65,507 byte datagram is just discarded. It cannot be completed unless you get all of the fragments. So the odds of one getting lost might be high depending on the kind of network you're on, or at least it's not trivial. And the only recourse we would have is to resend that entire block of 65,507 bytes. But there's a worse problem in that the client or the machine that's sending that datagram that's that big won't even know that the whole thing was lost unless we build something ourselves that re-requests it. So in other words, you could have a large chunk of data just disappear and have no way of knowing that it disappeared. So that can be a problem. And one of the solutions in real-time games is to avoid really large datagrams. In other words, if possible, we want to limit the game server datagrams to that 1476 bytes maximum that we have for, let's go back a second, that we would have for this. And actually that there should be 76 there. But the idea is limit the maximum size of those server datagrams to whatever the MTU is of the underlying network system. Now, one other thing to watch out for with that is if you have more data that you need to send than that, rather than sending it as one larger UDP packet, it's better if you divide it up yourselves and have different message types that you set. This is a message type that's like movement data. This is a message type that is some other kind of data. This is a message type that's some other data. So even if those get lost periodically, then they'll be followed up by another message. The other thing you want to do is rather than sending event messages like this key was pressed, this key was released, it's better to send here's the key state now, here's the key state now, here's the key state now, and repeatedly send that. So if one gets lost, you're only off by one message worth of the timing for knowing what that state is. We'll talk more about that in a little bit. Okay, so how do you program UDP? Well, it's still done through sockets, just like TCP was. There is a little bit of a difference here that's worth mentioning, though, that rather than using send and receive, we still open the socket. There's no need to call connect from the client end. And instead of calling send, we call send to. And the way send to works is you specify the socket you want to send on, you specify the buffer that you want to send, you specify the length of the data that's in that buffer, there's this flags, and then you specify this address that you're sending it to, and then this is the length of that address. And receiving is also different. Instead of using listen and accept on the server, you just do receive from. And that basically says, hey, on this socket, read this amount of data into that buffer. These are the flags. Here's the sock address that plugs in the remote address of who sent you that data. And then here is the length of that address when it comes in. So note that setting up the client and server are actually much easier than TCP in a lot of ways. We don't have to do listen. We don't have to do accept on the server. On the client, we don't have to call connect because we're just dropping packets onto the network. We're not really, or datagrams into the system. We're not really making a connection where they answer the phone. In other words, this is like sending postal mail rather than making a phone call where they have to answer and you have to be connected. So let's look at the programming needed for each of the client and server. All right, so I put them on one page here, so it's an easy thing to reference here and look at the difference between those. So let's look at the client first. So the client, we create a socket. How does that differ from the sockets we made before? It's address family INET still, but now it's sock_dgram here in the connection type instead of sock_stream. So that's a difference there. Also, we then fill in the address and port of the destination into some sort of address structure. And then we use send to send data, receive from to receive data from that socket. And then we use close socket or close when we're done with it. So in other words, notice how this is simpler. We just create a socket. Once that's created, we do send to an address, receive from that address, and that will get data from the TCP or UDP system that sends the data to that remote address, receives data from that remote address, and returns that back to us. Oops. On the server side, we create a socket, in the same way that we do up here. And now notice that we still have to bind the address to a socket, but we don't listen anymore, and we don't accept anymore. Those two function calls are gone. Once we've bound, we can then receive from and send to. Same functions we had up here. And then we can use close socket when we're done. So notice these are simpler than it was for a TCP server and client relationship because it's not connection oriented. There's no part where you had to dial the number, they have to answer. Now we have a connection, now we send data. The other advantage of this is over TCP is because this is not stream based, is when I drop a packet in here, if it makes it to the other end and gets received, the segmentation is there automatically. I know I have one packet that I just got, one datagram that I just got. I know that I can then structure that from the beginning of that datagram and say this is the start of it. At this offset, this data is. At this offset, this data is, and so forth. Okay, a couple notes about how UDP actually works. The send to function simply sends and is done. It doesn't have any confirmation that the thing was received. So note that just because the function completed and returned to us doesn't mean the data was received at the other end. It just means it was dropped in the mail, dropped on the network. the receive from function will block and wait for a datagram to arrive. And note that the default behavior of that receive from, where you say, hey, receive from, it'll block and wait for a datagram on that socket. When one comes in, it says, hey, I got a datagram from this person on the other end. And then the next time you call receive from, it'll block and wait again. In other words, if you say, hey, go out and check the mail, it'll go stand at the mailbox and wait until mail shows up. Now that can be problematic for a game client or a game server. You might say, well, why is that problematic? We want to get a datagram. Why not go out? If I say get a datagram, go get one and come back. Don't come back till you have one. But the problem is we might want to have the game continue to update its state at a regular interval, kind of like to think about the frame rate and render it, regardless of whether we got new data from the network or not. In other words, you don't want to have all the bullets slow down and stop because some client was slow. And in your game that you're playing on the client end, you don't want to have the rendering completely stop and everything gets sluggish and halt when the server is slow. So there's like some weird writing there. Let me fix that. So neither the client nor the server should, I don't know what was going on when I wrote this. It's late. Should just stop when nothing is available. All right, that looks better. Okay, so the reason that's problematic is we don't want the client game or the server kind of simulation of the game, the updating of the world, to stop when nothing is available on the network. The simulation should continue, and when messages arrive, it should handle them. In other words, it's like you go to the mailbox, if nothing's there, you keep working on what you're supposed to be working on. You go to the mailbox, if nothing's there, you go back to working on what you're supposed to be working on. If you go to the mailbox and a letter is there, you process that letter and then go back to working on what you're supposed to be working on. And that's the way we want to set that up. So the solution to that is to set the socket to what's called non-blocking. There's a non-blocking mode you can set to the socket. So when you call receive from, if there's something there, it'll give it to you. If nothing's there, it'll immediately return and say, I didn't find anything. Now, how do you set a UDP socket to non-blocking? Well, if you're in Unix or Linux or Mac, which is really a Unix-based operating system at this point, there's a function called fcontrol. And what you do is you specify the socket, and you do this setfl, which stands for file set flag. And there's a flag called O non-block. So you call fcontrol on the socket and say, hey, set the non-blocking flag for that socket. And if that function completes successfully, then now any subsequent operations on that socket, it won't block anymore. In Windows, it's very similar, except you use this IO control socket function that's part of WinSock. You pass the socket to it. In this case, the flag is FIO NBIO, which stands for File IO, Non-Blocking IO. And then you pass in this mode, which is 1, which is setting the flag to a value of 1. And if that succeeds, then it's non-blocking. But once the socket is set to non-blocking, any call from receive from will return a -1. Now, the return of -1 from receive from would usually mean an error. But in this case, if I have it set to non-blocking, then that return of -1 that always happens, we can tell if it's an error or it's some other error, whether it's due to non-blocking or some other error. And the reason for that is you get that return value of -1, and if error note is set to E again, or E would block, then that indicates that everything else is fine and there's just no data available. In Windows, return value of -1, and if you call WSA get last error, and that produces a value of WSA E would block, and these are just defined constants, then that indicates everything is fine, there's just no data available. So in practice, we can simply assume that in UDP, any return value from receive from that's less than or equal to 0 indicates an empty or non-existent packet, and any other value that's returned from receive from indicates that we got data, that we received data. So that gives us the ability to effectively poll the socket to see if data is coming in. We say, hey, receive from, and if it says gives a value less than or equal to 0, then we say, nope, there was nothing in the mailbox. In other words, if I go to the mailbox and I get a value out of the mailbox that's less than or equal to 0, that means there's nothing in it. If it's greater than 0, then, oh, I got data. So we can pull the socket and say, is there data? No. Is there data? No. Is there data? No. Is there data? Oh, it's greater than 0. Yes, there's data. Now I can process that. So to process all of those incoming packets, we might have something that looks like this. We might have, here's a kind of a packet structure, from address, from port, packet length. Here's the maximum amount of data we could have, 1476. And we have that struct packet, rx packet, rx bytes. And then here's a while loop that's going to process all the packets. We call receive from. And that returns the number of bytes received. If that's less than or equal to 0, we break out of this loop. If it is greater than 0, then we get the packet, we fill in the packets from address, we fill in the port, and then we would process the packet data here using the length and whatever's in this array down here. And then we loop back up. So this will repeat over and over again, getting anytime the receive from returns a packet, we process it, and once we run out, then we could exit the loop and do something else in our code. Now, the idea here is we just need to decide how to put our game data into the packets. In other words, into this array here, this array of, and really you could make the UDP packets larger, but you risk that fragmentation problem. So generally we'll try to keep it below this size. So we need to determine how we're going to stick game data into this array, into this packet data array. So how do we do that? And it turns out that there are a number of options for how do we encode the game data to send it across the network. And that process of encoding kind of binary game data, variable data, and sending it across the network and then decoding it is called serialization or marshalling. And what that involves is saying, hey, here's this data object or this array that's in memory, this data that's in memory, this structure that's in memory. I need to send that to the other end, and then I need to put it, take it out of that packet and put it back into some data structure on the other end. And the idea there is there's several options for serializing that data. One is binary. In other words, you send a block of memory for a structure or array directly. There's no encoding overhead, but there can be problems created if you have architectural differences on the server versus the client or the two ends. In other words, if you have one system that implements things in little endian, on a little endian architecture, where it's least significant byte, most significant byte for, say, a 16-bit integer, and one of them is big endian, where it's most significant, least significant, then when we just transfer that in binary, you're going to end up with the wrong values on one of the two ends. So you'd have to write some code that does that. And we're kind of doing that back here. Remember where we have this network to host short thing here that we're calling. It's kind of what that function is doing, is making sure things are in the right byte order. So binary tends to have that. If your server and client are always on the same architecture, always on, for example, a 64-bit x86 architecture, or 64-bit, I guess it would be x64 architecture, then everything would work fine. But if you have something that's running on mobile, that's on an ARM architecture of some sort, and something else that's running on, the server is running on some sort of x86 architecture, then you might have a problem with using binary. So binary tends to, it has very low overhead, but it tends to be, because there's no encoding or decoding involved, but I would suggest being cautious when using that. Also, another option is a custom serialization, where you come up with your own way to encode the game data. That could be text-based, could be binary, not standardized. There are a number of ways you could do that. Another one that's pretty heavily used is JSON, which is a standardized, more human-readable way of serializing objects. And that's JSON, that's JavaScript object notation. It was designed for that. It was designed for web apps to transmit data from one machine to another machine, which makes it very much appropriate for sending data across the network. And it also has the advantage of being human readable text format. But the problem with that, with JSON, is it's not necessarily as compact as if we did it in binary or made our own custom format. And there's one other option I'm going to look at that's a little more compact as well. So the idea there is it does create this human readable text format, and it's a standardized way of doing it, but it's not as compact or as fast as other methods might be. And that brings us to message pack, which is one that I've used before. And message pack is kind of this third-party, very compact binary serialization format, and it's fast, compact, and language independent. In other words, there are message pack encoders and decoders for a variety of languages. Python has one, C language and C++ have one, JavaScript has one, Java has one. So they're implementations of message pack, and it's kind of an open spec serialization methodology. So if you have some language that doesn't exist for, you could look at the specification and write your own. And it's actually relatively straightforward to do that. And this is actually a good choice for encoding and decoding network game data, because it would allow us to use different languages on the server and client. It would allow us to have it be, so it can also be cross-language. We could write the server in Python, the client in Java or C++ or whatever. And there is one other format that I've seen, and that's XML. You may have seen XML files, but that's a standardized way to store kind of hierarchical structured data in a text-based human-readable format. But it is human-readable, but it's complex and not compact, and it can be slow. So it's really slow, not compact at all. So the one I like for game data, especially real-time game data where you have to keep the size small, would be either message pack or some kind of custom or binary format. Although message pack can actually, in some cases, create a something that's smaller than even the binary. Okay, so for our game server demo that I'm going to do here, that I'm going to write some code for, I'm going to use Python. Because that's going to allow us to focus on kind of the higher level concepts without writing all of the low level UDP code. But note that we could, however, use C and C++ or any language that supports sockets. We just have to be able to create a socket, call send to, call receive from, and close the socket. So before we dig into the code, I want to spend a little bit of time looking at how do we send and receive UDP packets in Python. So I want to look at that from both the client and server perspective. So let's start with the client. So here are some code snippets from some Python code that does the important part. So setting up the socket, we import socket. We call socket.socket to create a socket object. And this works just like the function call that we would call in C. We pass in AF_INET, which is a value that's defined in socket, so socket.af_INET, and we pass in sock_dgram, which is another one. So notice that looks exactly like what the C code would look like. Call the socket function, in this case in the socket module, pass in AF_INET, pass in sock_dgram, and that returns to us the socket. Once we have the socket, set it to non-blocking. Now this is abstracted out, so we don't have to worry about if we're on Windows or Unix. So we can just say client socket.setBlocking 0. That 0 or false means it's set to non-blocking. The next thing we're going to do is set our address to bind to. We just say server. We don't even have to This is the client, so we don't have to bind. But we're going to set the address of the server. That's who we're going to connect. Connect is the wrong word. That's who we're going to send our datagrams to. So we set up the address. In this case, I put in localhost, and I put in a port of 12,000. And then I create my message, and then I can do a send to. I can say, hey, on the socket that we created earlier, send this message to this address. Now, there is one thing I'm doing. I notice I'm doing a message.encode, and that's because strings in Python 3, they defaulted to Unicode string, and we need to encode that, and I'm using UTF-8, which is kind of the 8 bits per byte encoding for that. You could also do a message.encode in what's called Latin, which is kind of uses ASCII encoding. But in this case, UTF-8 is how we'll encode that with 8-bit bytes. And so in other words, we're sending this message of 8-bit bytes that says hello to this server address that we set up there. Notice we did not have to connect. We did not have to wait for a connection. We just basically said, hey, here's the address of the server. Write it on the envelope, throw it in the mail. Now, this message will not get fragmented, notice, because it's only this string hello. That's all of the entire message. So it's not going to get fragmented. And to receive a message, we're going to call this message address equal client.socket receive from with a maximum value of, in this case, 1476, since that's the largest one we could see. And if when this returns, it's going to return to us the message and the address. Or if this fails, because it can fail if there's no message there, because we set blocking to 0, this will fail when there's nothing to receive. I'll set the message and address to none and none. And then down here, I'll say, hey, if the message I received was something other than none, then I got a message. So here I would process it in some way. I'd take that message that I received, do something with it, and I also know who it came from because I get the address of who sent me that message. Now, let's look at the same kind of code on the server. The server is going to, again, import socket, create a socket, af_inet, sock_dgram, set it to non-blocking. Server address, set the port to 12,000. Notice that empty quotes in there is going to use whatever the local machine's address is in this case. We could put 127.0.1, or we could just leave it blank and it'll use the machine address of the machine we're on. And then I do a server socket.bind. Now I do have to bind this socket to that address on the server side. The reason I don't have to do that on the client side is because when I say send to, it'll just give me a local port number and send it on whatever. It'll kind of just pick a port number that's available and use it. Over here, though, since we need to be listening on port 12,000 and receiving that, maybe I shouldn't use listen there, but I need to be waiting for incoming traffic on port 12,000. I need to bind to that address. After I've bound to receive a message, same thing I did on the client side. And then to process it, same thing we did on the client side. And then to send a message, same thing we did on the client side. So the only difference here is that we have to bind to receive stuff on the server side. Okay, so now what we need to do is just decide upon a protocol for our game server. In other words, what is the data that we're going to send? What's the data that we're going to receive? What are we going to do with that data? And so the basic idea of the protocol for a game server is going to be something like this. We're going to send input and control events from the client to the server. In other words, the user presses a button. The server needs to know about that. A button that controls the character in the game in some way, controls the action of the game. Spacebar, tell them that the player jumped. Or mouse click, tell them that they click the mouse to fire. Moving the mouse left or right, tell them that that's changing the player's position that they're traveling in the world, the direction they're traveling. Press the W key, tell them that we're running forward in the world. So we need to send those input and control events from the client to the server. The server is then going to, which is going to maintain the game state based on that client input, is going to then update things based on that input. In other words, you press W, you try to move forward. We send the message over to the server that says, hey, player 1 pressed W, they're trying to move forward. The server is then going to update player 1's position in the world. The server is then going to send out after it does the update of where everything is in the world, it's going to send out a game state update to the client saying, here's where everything is in the world. The client's going to receive that. It's going to render to the screen based on that. And then that process is just going to repeat over and over again. Now, there are a couple other concerns on the server of things we need to do. We need to wait for players to join. In other words, if it's a multiplayer game, we need a way to have players join the game either all at once before the game starts or as the game's playing, people join, people leave in a more organic, dynamic way. We need a way to handle that. We're also going to need a table of currently connected player addresses because we have to send this new game state data out to all of the players on the game. So if we have 5 players that are connected, we have to get messages from them saying what their input was, update the world, and then say, hey, everybody, here's what the world looks like now. All of you render that. We also need a way for players to exit the game when they're done or time out. In other words, if their network connection goes down, we might wait for a little while, but if I don't get a message from them in a certain amount of time, then we should boot them off the server. Stop sending them things if we haven't heard from them in 10 seconds or 5 seconds or something like that. Now, both the client messages coming from client to server and the game state data going from server to client will have to be encoded in some way. And like I said earlier, you could use JSON, Pickle, XML, struct.pack, whatever. I'm going to use message pack for the example that we're going to do in here because it's compact, fast, language independent. So we're going to look at how to do that. So here's what we're going to build when we get to the code. We're going to make a game client loop. It's going to get user input events. It's going to then send the user input event to the server if there was a change in user input. It's going to do that with a UDP packet. And if data arrives from the server, that's going to be game state data. So we're going to receive that. We're going to decode it. And then we're going to process that and update any of the local game state variables based on what came in. And then we're going to render the display. And we're just going to do that over and over. In other words, get user input, send those to the server. When we get an update from the server saying the new game state, process that to update all the local variables, and then render that on the screen. Repeat. Now on the server, we're going to receive client events. If we receive a client join event, we add them to our client table. If we receive a client exit event, we remove them from the client table. Any other event that's not a join or exit, we process it. In other words, it's going to be user input events. We then run our simulation of that frame of the game state. So we update the game variables. Let me make that plural there. Update any of the game variables, the X, Y position of each player, the number of bullets, the state of what items are available and where they are in the world, and so forth. And then we're going to send that out to all the UDP clients in the table, and then go back and receive more client events. So in other words, if we get an event, we process it, update the game state, and send out the game state to everybody in our table, and then we repeat that over and over again. Now, there are some potential problems with if we set this up wrong that we should consider. So again, since UDP only sends datagrams and it's an unreliable service, we have the potential for some things to go wrong here. So in other words, events could be lost or received out of order. We need to think about that. The game state responses could be lost or received out of order. In other words, you could have a game state where stuff goes, player 1 is traveling along a path. It's here, it's here, it's here, it's here. If those get out of order, you might have a case where it goes here, 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 back to here, over to there, and things will look funny. So we need a way to handle cases where if we get a outdated state packet, what do we do with it? Also, different event types have to be sent, maybe at the same time. In other words, a keyboard event and a mouse event might happen in the same frame. We might want to send both of those. Different game state updates must be sent repeatedly. In other words, the game state, you can't just say, hey, everything changed to here and then wait for things to change again because that packet could get lost. And the other thing is that if the game state is really large, multiple fragments are needed, or we need to come up with our own way to segment that off and fragment it. And we have to be quick about how we do those updates. All right, so to begin making our protocol, let's pin down some protocol messages. So let's think about what needs to be sent from the client to the server. And let's keep it simple for right now. Let's say we have key down events, key up events, a join, an exit, and then a keep alive. And a keep alive event is usually a way to say that even if they haven't pressed a key in some time, that they're still connected. It's a way of saying, hey, I'm still here. I'm still here. I'm still here. Rather than saying, hey, nobody's pressed a key or made any mouse movements, so I'm just going to sit here and then time out, and the server will think that I'm gone and it'll close me out. So that's what a keep alive event is. And we also need to think about what keys we need to support in this, because we can't just say, hey, somebody pressed a key. We need to say pressed this key. And maybe we don't want to send along all of that. Maybe some keys are for local things, like changing the size of the window, or bringing up a local menu to turn sounds on and off or something like that. So some of the keys will be sent. Some of them might be local client-related keys. And then from the server to the client, we need to decide what data we want to send as far as the objects. Maybe the list of players and where they are in the world and how they're moving. Maybe a list of bullets and where they are in the world and how they're moving. Maybe the list of items that are available, health boxes, treasures, inventory items, and where they're in the world. And then maybe some other data. How much time is left in the level? What are the current scores? Like things that other data that might need to be sent. Maybe DM chat messages from one player to another player. We need to be able to send that kind of stuff too. Now, again, all the game objects should likely be part of the same game state, and they need to be encoded in some way to be sent, and we should try to keep that to that 1476 boundary. If we can't, then maybe we send these as separate datagrams. Here's the player list datagram. Here's the bullet list datagram. But if possible, it's best to stick all this together and keep that to that size, below that size, or equal to that size. Okay, a couple other things that we need to consider, which we've mentioned these before in some way or another. So we need some kind of plan for lost event packets. In other words, they press the W key. What if that datagram that says W key was pressed down gets lost? Or what if the W key released gets lost? What if one of those events gets lost? Also, you probably want to plan for out-of-sequence events, meaning, like I said earlier, the game state, you get state, let's say 100, 101, 102 is what's sent, but we get 1 of 3, 100, 101, 102. It's going to look like things jumped around in the world. So we need to plan for what happens if something comes in out of sequence. We also need to plan for users dropping out, their network going down, their boss walks up behind them and they close the game really quickly, whatever. Teacher walks in the room and starts the lecture. Lightning hits their telephone pole and or windstorm happens and a tree falls through the fiber optic line and they lose their connection. And there are some kinds of packets that might need to be acknowledged in some way. Okay, so I'm going to pause here briefly. We came in under the hour that I wanted for this, but I'm going to come back and rather than writing the code live, which is going to take a while, I'm going to demo some code that will be posted on the course site. We'll look through the code and look at how it's organized. So I'm going to go ahead and write that up, and then I'll be back in a little bit. And then I'll walk you through it, and then we're going to look at some of the shortcomings, and then we're going to add a little bit to that code to fix those shortcomings in a couple versions. But we'll look at the code, we'll demo it. There'll be both a client and a server. We'll look at how they're set up, how they work, We'll look at those shortcomings. We'll fix them. We'll look at that. We'll fix those. So we're going to kind of iterate through a couple of these different versions, and then all of that will get posted to the course site for you to look at and play with. So let me pause for a second here, and I'll be right back. Okay, we are back, and I've got some code that I want to run quickly and show you. So let me bring that up, and let's go through it. So let me switch over to where you can see the code that I have on my screen here. Okay, so let me adjust these so you can see. A little bit better here. So that is going to be the client code. And let me make it so that pretty much fills up the left side of the screen. Let me scroll that up to the top. And I've tried to add some comments to this to make it a little easier to follow, including what the shortcomings are. Okay, so there's that. And then on the left is going to be the client, on the right is going to be the server. I'm just adjusting the size. Maybe I should have done this before I resumed. Okay, so there's the server. So let's start with the client. So the client, and notice there are problems with this implementation as I have it now. Like I said, we'll fix it in a little bit. But a quick overview of what the problems are. There aren't any keep alive messages. The event system datagrams, the way I've set it up, they could be lost and then we'll miss an event. The event system datagrams could arrive out of order. I'm not handling anything with the ordering of those. And only one datagram is handled per loop iteration on the client. And we'll talk about why that's a problem in a second. There's also no client-side prediction, meaning that as we're moving the items in the world, we're waiting for the server to tell us, hey, where are the bullets, or where's the other player? Where are they now? Where are they now? Where are they now? And if the network slows down, then the positions of things is going to kind of jump around in the game. So it might be here and then over here and then over there, rather than a nice smooth animation of the spaces in between. And maybe you've played games where it starts to look chunky like that when the network slows down. But if you do client-side prediction, you can kind of fill things in, and then when you actually get a packet, maybe it was a little different than what you predicted, but then you would slowly adjust from there, and things will look much smoother and more pleasing to the user. All right, so let's go through this code. Notice I am using message pack, so I imported that. To install message pack yourselves, if you want to play around with this code, you can use pip, the pip tool, which is a Python installer package, and Python package installer, whatever they call it. But use the pip module, say pip install message pack, and you can actually do that directly from the command prompt as well. Let me quickly show you how you could do that. Let me do run a Python shell. So if you want to install message pack from the command prompt here, you can do import, I don't know what that says, import pip._internal. And this is doing it through the command, or not through the command prompt, but through a Python shell. And then I can say pip._internal.main. And then to main, I can pass in a list of install message pack. And notice that I already installed it on here, so it says it's already satisfied. But if you don't have it installed, then it will go out and fetch it, it'll download it, it'll go through the install process, it'll get any dependencies that are needed, and then it'll say, now it's installed. Notice this is bitching at me that I need to upgrade my version of pip, but whatever, I'll worry about that later. All right, let's continue through the client. So on the client side, I basically have created this player client class. And that's what I'm going to use to keep track of that player. Now, that's like kind of like the player object. In other words, it has their X position, their Y position, the name of the player, the speed that they're, the size of the player. In other words, how big are we going to render it? The speed that they're traveling or that they can go, and the color of the player. And notice here you could have different colors. You could have like pants color, and shirt color, and head color. You could also have like a selection of different, I don't know, since this is a kind of a 2D game that we're talking about here, maybe a selection of different avatar sprites that you could choose from. You could have that set. But in our case, we're just going to use a different color for each one. And then down here, notice that I have this dumps method and a loads method. And what those do, or those are what's going to serialize the data for this player. In other words, here, I'm creating a dictionary. I'm sticking in the X and the Y and the name and the size and the color, the things that I would want to transmit. And then I have this message pack.dumps of that I'm calling, which message pack.dumps, that's what actually does the serialization. So I'm saying serialize this dictionary and then return it. And then loads just does the opposite. It unloads that thing into this temporary dictionary, and then it sets the parts of this thing. So when I receive a message from the server that has information about some player client, and it tells me their X and their Y and their name and their size and the color, anything that I need to know, it fills that into those attributes of that. My cat is scratching at my leg. It fills it into those. It fills it into those attributes for us. So in other words, these are kind of opposites. Dumps puts it into that serialized format. Loads takes it from the serialized format, puts it back into the attributes of the object that need updated. And if you wanted to add more attributes to this, like, I don't know, score, hit points, experience points, armor class, whatever, you would just add more things to this temporary dictionary and more things to the loads part of that pulled them out of that dictionary. And then we have a really simple render. In this case, we're just drawing a circle to represent the player. But now I've defined a couple of functions, which is a net send message. And you'll notice the way that net send message function works. I've added something to this. And I would recommend, if you're making a network game system, I would recommend that you do something like this. And what this does is this is code that I added to simulate lost packets by randomly just discarding stuff. So I'm going to go ahead and comment this out for now. But this is a good way to stress test parts of your code. And that is to say that rather than just trying to run this on a crappy network, simulate running it where, in this case, 1 in 10 packets gets dropped, or 1 in 100 packets gets dropped, or 50% of them get dropped. And what I did here is when I call send message, net or send net message, you can just have a random number that when you call it, rather than sending it, it just ignores it. And that allows you to test on a local host or a LAN where you'd be unlikely to get any data loss. Test what happens when you have data loss. Another thing that I might suggest doing that I've done when testing network code like this is sometimes it can be useful to test varying latency times. So in other words, you could have in this net or send net message, you could actually spawn a thread that waits a little bit of time and then sends it and then closes. And that can be useful as well. In other words, wait for between 0 and 1/10 of a second before you send this to simulate delays in the network of those things. But I really like this way of testing, stress testing network code, because it simulates networks that drop a lot of packets. I'll comment that out for now. But essentially to send it, we're just taking our socket, the client socket, sending to the server address that message, encoding it with UTF-8. Now the get net message does the opposite. It tries to get a message from the client. In this case, I'm only receiving up to 1024. I could put the 1476 there if I wanted to, but I'm trying to receive up to that number of bytes. and I get the message and the address of who that message came from. Or if there was none available, I get nothing. I get none and none. And then I return those two things. And now the process net message function takes one of those messages and that address that came in from here, and it basically says, hey, take that, use message pack and do a loads on that message that came in, and put that into the player list string, because that's what's being sent on the server end. And then player list, go through the player list string and do new player.loads for each of those and append that to that player list. Now down here for the main program, here we are creating the socket. This is just Pygame stuff up here. Here we are creating the socket. Here we are setting blocking to 0 so it doesn't block. Here we are setting the server address to localhost. And here I am setting my player, and then I immediately after I set my player name, I send a net message to join to that. Now notice the message I decided on looks like a HTML tag that has inside of it join : and then the name of the player. That's what I decided on. So that means on the server side, I'm going to have to write a processing part of my process net message function that looks for a join event and then adds that player name to the table if it doesn't already have them, or if they're already not in the table. And then here, player list starts out as empty. We then enter our main game loop, and what we do is we say, hey, for every event that I get in Pygame, process it. If it's a quit event where they press that, set the game running to false. If it's a key down event, and it's the escape key, then set game running to false. Otherwise, send a key down event. So here I'm sending that event, and I decided the structure for that is same kind of tag structure, but KD stands for key down instead of join. And then I put the string of the key in there. So I'm putting the actual type of key that it is in there. And then if the event type is key up, I send a KU event. Notice I added these comments here. Be careful, datagrams could be lost. And I actually describe, hey, maybe there's a better way to do this to handle input events where if we, and notice that it could be very bad if we lose a key down event. If we lose a key down or a key up event, we now think the key is in a different state on the server than it really is on the client. So we probably want to think through a better way to do that. And then down here, what I do in my main loop is I get one message from the network. I process that message, which in this case is just getting the player list, because that's all I'm sending right now, and processing that. So I receive, and then after I get that message, if the message was not none, in other words, if there was a message, I process it, which updates the positions, everything, and then I just render all the players in the player list. And notice the player list is going to be updated every time I get a message that has where all the players are. Now on the server side, it's kind of the same thing. I have the same kind of player object that I had over on this side. Actually, let's synchronize those and look at the two. Here, rather than calling it player client, I'm calling it player, so it's distinctly different. But notice I've added some things. I need to know what IP address that player connected from, what port they connected from. And then down here, I'm going to keep track of what keys they have down right now, because I can't just call the get key function over here to know which key is down. So I'm going to actually look at that right now, maintain the state of what keys are down. When I get a KD event, I'll add that to the list. When I get a KU event, I'll take a key out of that list. So notice I put comments on those to show which ones are on the server side only. The rest of this, the dumps and loads, works the same. But now I have a move in here as well that moves the player around. So if A is in the key down, I move them to the left. If D is in the keys down, I move them to the right. If it's W, I move them up. If it's S, I move them down. And here, self dot, I make it so that they can't leave the screen. And then my render is essentially the same. And you don't really even need the render on the server. I added it so you can see what the server looks like and how it's tracking things. My get net message works the same way. Send net message to a client works kind of like the send net message did over there, but I need to say what the client address is. And there we could add code to simulate lost packets again. I have it taken out here. And then here, process net message. If the message starts with a square bracket or an angle brace and ends with an angle brace, or greater than, or less than and greater than, I guess, then I trim the message out, and if it has a colon in it, then I split on that colon, and then I look for what kind of command it is. If it's a join, then I add them to my player list. If it's a quit, then I remove them from my player list. If it's key down, then I go to that player in the player list and I add that key to that. If it's a key up, then I go to that player, the keys down array in the player of that address, and I remove that. And then I have this player list.dumps function, which takes the entire list of players that I'm maintaining on the server, puts them all into a serialized form using dumps, and I send that whole thing, and that's what's being received over here in this process net message down here. So notice over here I'm putting this player list string in. That's what I'm sending, and over here I'm getting that same player list string out. And then I'm updating all the players on this end. And now you'll notice in my main loop over here on the server side, well, first off, opening the socket, I have to add the bind. I don't have to do that on the client, but I did here. And then down here, I have my loop that's running. And this side, the only keys I care about, or early events I care about, is escape to close the server, or clicking the X to quit out of the server. And then other than that, I get a message. I process the message. And then I update the game state by moving all of the players to their next state. I then create the serialized list of where all the players are. And then I have this loop that sends it out to all the clients. In other words, this is exactly what we talked about in the thing. We update the game world. We then create a serialized version of the game world. We send it to everybody. And when they receive that, they know where everybody is in the world. And here, just for fun, I went ahead and rendered everybody so you could see that on the server. So let's go ahead and run this. So I'm going to run the server first. And let me move that over to the side here where the server lives. All right, so there's the server running. And actually, let me put that up there. And here's the Python shell that goes with that. Let me put that down here below that, so you can see what's getting printed on that and see what's happening on the server that goes with that. And now let's run a client. And remember, when I run the client, it's going to join with a player named Paul. Let me go and run that. And let me minimize this. Let me bring that down to there so you can see what's going on the client side. And then here's the client. All right, so now I'm going to click on the client window here, and I'm going to drive this around a little bit. Now you'll notice that it is moving around, and it is tracking that. But you may have noticed at the very beginning, I don't know if you can tell, but it's a little bit, it feels a little sluggish. And part of the reason for that is the only way I'm seeing my position update on this side is if I just watch the client side and I'm going to press now, and so press down now, release now, press down, release, press, release, press, release. It feels a little sluggish and not smooth like I'd expect to be. And actually, if I hold that key down, it looks a little kind of chunky. But it doesn't look or feel smooth the way it is right now. And part of that problem was, remember that I talked about that we're only really receiving one message, network message, every time through the game loop. And it might be, and that can create a backlog of those. And actually, let me see if I can run 2 clients. Let me move this guy down so you can see it a little better. So let me go to where that code is. Let's see. There it is there. Let me run another one of these. Okay, that didn't work because stupid reasons. That's because I have multiple versions of Python, and apparently the version of Python I tried to run in. So let me start another one of these. Give me just a second. Okay, so now I have 2 clients running. Let me hide this so we can see all of this at the same time. So now I have 2 clients. So let me click in this bottom one. And when I move that one around, notice the delay on that bottom one. I don't know if you can see that or not, but you'll notice that they're not really well synchronized. Sometimes they are. Let me switch to the top one. But you'll notice it doesn't look really smooth. And part of the problem, and these can also kind of get behind on the messages. Oh, that was moving nicer there for a little bit. Now it's back to being a little more chunky looking. And that's, if you go back and look at those things that I wrote at the top that said that there were some issues with this, a couple of the issues that we want to fix are this kind of sluggish filling up. So the whole idea behind using UDP was to make it so it was very real time and didn't feel sluggish like this. And yet we're still having that kind of sluggish behavior. And so we want to come up with a way to fix that. And so the main things that we can do to fix it are, number one, I'm going to add a really simple fix to this that's going to essentially read all of the events that we have in our message queue rather than just once per time through the game loop. And the more clients that we get in here, the more problematic that it will be. But let's go ahead and add that code first. So rather than through the game loop only reading one of those at a time, which can allow us to get behind. And here, let me exit with this client down here. So on this client down here, I'm going to go ahead and hit escape. And notice it took a while for that to go away out of that one. So what I'm going to do here, I'll escape out of all these. And notice it took a while for it to leave the server. But you'll notice if I look at that server kind of console output, you'll notice it says added, and this is because we had the same name on each of these, added player to list. Notice it's keeping track of what address they came from, but also what port they came from. And those ports are assigned automatically. And then when I exited, it shows who left and it removed them from that player list. Okay, so I'm going to pause again. We're going to, well, actually, let's just fix this live. So I'm going to just fix this live here. So the first thing I'm going to do is I'm going to make this work a little bit better. And here, let me go and exit the server too. So I'm going to make it so that in the server code, I'm going to handle all of the events that come in. And notice that here was where I did that right here. So how do I process all of the messages come in? So let's fix that. I'm going to do a while loop and say while true. Get a message. If the message is not none, then process it. But if the message was none, that means there wasn't a message for me. So here I'm going to say else. Let's just break out of that loop. That's kind of what we talked about in the presentation in that little C code snippet we showed. Was, in other words, enter a loop that processes all of the messages that are coming in and then breaks at the end. So rather than doing one and then rendering and then another message and rendering, which is going to allow us to get behind on processing this. Let's process all of the network messages and then draw the screen. Now let's do the same thing on the server side. And it's probably even more important on the server side. Reason being that we might have dozens of clients that we need to deal from. We don't want to like read from one client, update the game state, read from the next. We want to read from everybody and then update the game state. So here, let's do a while true. So notice we can do this in the same way. Else, break out of that loop. So this would allow us to read all of the messages and do that. So let's run this and see if the performance looks any better. Okay, so there's the server side. Move this over here where we can see it. Now let's run the client. And there's the client. And now, as we move around, there'll be less chance of that getting behind. In the client and in the server. All right, so let's pause there for a second. And before we pause, let's go back and look at what the shortcomings of this were, of each of these were. And this is also might be a little slow right now because I'm also recording on this machine. But notice that there's probably another thing that we may want to deal with, and that's we may be overloading the network system by sending packets and packets and packets as fast as we can. We may want to put some sort of delay in this code that right now we're sending out this network data as fast as we can here. Notice that there's nothing controlling how fast this game loop is running. So I might add some code to do that here. Actually, let's do that before we exit this. So let's limit this game loop. So one thing we can do is just add a delay at the top of the loop. But I'm going to do it with a frame clock. So let's do FPS clock. And those of you who've programmed in Pygame before might be familiar with this. But let's do Pygame dot time dot clock. That creates a clock object. And then at the top of the loop, I'm just going to do an FPS clock dot tick. And I'm just going to set this to an update rate of 30 hertz on the server side. So in other words, it's only going to do this 30 times a second. And let's do the same thing on the client side. So in the main loop on the client side, let's do FPS clock equal pygame.time.clock. So we create a clock object, and then we tick that clock at FPS update of 30 on that end. All right, let's run each of these again quickly. So that restarted the server. Okay, there's the server up and running. Now let's come over here and let's restart the client. And there's the client, and now let's move that guy around. And you'll notice it moves much slower because we're moving it only 1 pixel at a time. But you'll also notice it moves much smoother, that there's no weird jitteriness to it. And so if I want to move it faster than that, then in my server simulation code over here, let me escape out of the server, escape out of that guy. So in my server simulation code over here, I can actually base that movement on time, or in other words, just increase the speed from 1.0. Let's make this like 4.0. All right, so let's run the server. Run the client. Let me find where the server window went. Oops. Stop that. Server. Let's move the server window over here so you can see it. Here's the client window. And now you'll notice we have something that's moving at a nice smooth pace. We can adjust that speed if we want to. But now notice it's not jittery or weird, and we're not overloading the network system like we were before. Now we're still not doing client-side prediction. So let's take a quick look at the shortcomings of this. No keep alive messages, event data system datagrams could be lost, event system datagrams could arrive out of order. Only one datagram handled per loop iteration. We fixed that on both the client and server side. That was a good fix. There are some other things to be fixed here. Client-side prediction, we could have the frame rate run much faster, but then only send out network or receive network messages as they come in and then synchronize them. That can make things seem smoother, because right now, the way it's written, the only time that we see and notice that join message gets sent automatically. That could be lost as well. That's another problem that we are not addressing. But notice now we have that moving around, and it's tracking that on the server just fine. But the only time, even on our end, that we see our position updated is when we get a message back from the server. Our state of this thing is being drawn only when we get the message state, or the game state, back from the server, which includes that entire player list. All right, so I'm going to pause for one more second. We're going to make a couple more changes to this code base to look at another version of this, and then we'll be back shortly to take a look at that. So let me pause, and then we'll be back and look at those changes we made in the other things. So hold on. Okay, we're back again, and I have a server here that I've updated some code on. It's very similar to the code we had before. So let me just scroll up and we'll look at some changes there. One of the things that I added to this one was, well, first off, I changed the so you can tell the difference when you're running one and the other one. I added a face to the little player, so they look like a face now instead of just a circle. But another thing that I added to this was that the game state, rather than just encoding that player list, I actually added it to a game state dictionary. And the reason I did this is going to allow you to really extend this and add other things to the game state. I'm still handling the events the same way, so those can still be lost and create problems for us. But over here, the part that's important is creating the game state dictionary. In other words, I'm still maintaining this player list, but I create this game state dictionary, which starts out in the loop as empty. And to that game state dictionary, I add the player list, the player dictionary list, and I add that item that I created up here, that list of all of those things. It's a list of player dictionaries. And I add those to this list, and then I add that to this game state thing like that, and then I basically just use message pack to encode that entire game state dictionary. And then and the reason why I did that is, notice that I have this comment here, you could add other things to the game state dictionary. In other words, if you had the bullet dictionary list, you could add that. If you had the item dictionary list, you could add that. And then as long as we're just using message pack on the other end, that anything we stick into that game state dictionary on the server end is going to magically pop out on the client end into that dictionary structure on the other end. All right, so let's look at these two. So let's go and run this. Let me run the server first. And notice I'm not really sending bullets or anything else right now. I'm just sending that. But there's the server that's running. I'll put it down here. Let's run the client. There's the client. There's my face. And there it is running around. And you notice that looks pretty smooth most of the time. We're still not doing client-side prediction. But you'll notice that I can still move that player around. And the server gets it, and I see it on the client end. And when I exit, it removes it from the server. Okay, so that's version 2 of this. And I want to do one last thing here where I show you a different way of encoding this. So this is still using message pack for the encoding, which can be pretty compact. But if we wanted to do a more native encoding, like a binary encoding ourselves, we could use struct to do that. So let's look at one final example here. I know I'm coming up on I'm actually over my hour and a half I wanted to be at for this video. So let me pause this, and I'll just load up the code that has the struct version of this, and then we will we'll stop after we look at that, and I will post all of these to the course page. So give me just a second. Okay, so here we are with this final version, and I imported in the server. I imported struct, and I used struct to show you how you can encode data. It's not actually; it's still using message pack for sending the data across. But I wanted you to see how struct can actually be used to serialize data. But you'll notice that this is now fairly responsive. It works fairly well, including if I add another client to this. And so if I were to add 2 clients, let me try to do that real quick. Let me start another. I should already have another one of these open. I don't know. Let me go ahead and create a new Python shell here. Yeah, it's in the wrong place. Let me go to that real quick. This is client 3. And let me run that real quick. There we go. Now let me make it so we can see both clients at the same time. All right, so there's the two clients. And move this guy down a little bit. And so here's client 1. That moves that one around. Here's client 2. Moves that one around. And notice this code still has problems. We still don't have keep alives. We still don't have client-side prediction, which means if the network lags, then we're going to see the player on the way they're rendered slow down and not work very well. But you'll notice that it does work as this is the server over here running. Here's client 1, they can play. Here's client 2, they can play. And you could very easily make this into some sort of network game where they shoot bullets. And notice it's very easy at this point to add bullets to that game state dictionary and have those go across as well and have those get updated by just adding things to the game state dictionary down here, like the bullet list. And so I'm going to go ahead and stop there. We're a little bit over where I want it to be time-wise. But that's the basic idea of how you can do game servers. And you'll notice that the two players pretty much see the same thing for the most part, whether we're on client 1 or client 2. And if I had the ability to control both of these at the same time, I would. Now, and the cool thing about this is this code would work not just on a local machine with a server running locally. I could use this across the internet. So I could run this server program on a machine that's visible to the internet that has a static IP. And then I could have these move around and be run anywhere in the world. Now, the farther away we are, the latency is going to get, so the more important client-side prediction becomes, the more important it becomes to make sure that dropped packets don't create a problem. And just as a quick thing here, to test that dropping of packets, you could comment in that code that I took out earlier, where it just randomly dropped 1 in 10 packets or 1 in 100 packets, and you can see how that affects your performance. And I would encourage you, if you are going to write network code, that you should stress test it. And one of the ways to stress test it is by doing exactly what I said. So rather than saying, well, how do I test this on a crappy network when I don't have one? Simulate it. Add in some parameters to simulate that. And that can be tremendously helpful. All right, so I'm going to stop there. Let me close all these guys down. You'll notice that when I close down, that guy goes away from that. When I close that, he goes away from the server there. And there's the server shutting down. And you can see those events coming in as they happen. Okay, so that's it for today. Let's switch back to the presentation for just 1 second here. And we looked at some code. There were still some shortcomings in that. I am going to have a lab where I allow you to fix those shortcomings in that. I'll probably have some chance for some bonus points on that lab as well. And I will post all of this code that we went over today to the course page. So that's it for today. Everybody stay safe. Work on your previous labs with the HTTP server. We really only have a couple weeks left. So there are some kind of finishing up topics I want to talk about. But other than that, we're getting to the point where we're going to have time to work on the labs, time to go over the study guide for the final exam, which will get posted, and start getting ready to finish things up for the semester. And everybody stay safe. Shoot me an email if you have questions. And other than that, stay safe, and I'll see everybody soon.